Thank you very much, and a very, very good morning to all of you. In my introduction, I was presented that I spent actually my first 20 years in academia at the University of Illinois and Northwestern. And I just look back, and actually I have been attending DAC for the last 40 years. My first attendance at DAC was 1986. In those years, I used to work on parallel algorithms for CAD. And we are a bunch of researchers doing work on HPC, and in industry, nobody cared. So it was basically a very academic work. But today, as CTO at Ansys, I'm proud to say that the HPC business at Ansys is about 15% of our revenue. And you can do the math. I mean, we are a $2 billion company. So it takes 20 to 30 years to take research innovations and make it into impact into industry. And today, I'm going to talk about another technology, AI machine learning. And I see that at this DAC, there are so many papers being presented by academics. And I have no doubt that it will have a very, very significant impact in the world of EDA. But I'm going to focus on the specific area of simulation. So I know at Design Automation Conference, you primarily know about sort of electronic design automation. But Ansys serves in the space of electromechanical, physical, all kinds of different products. So I wanted to give you a big picture of the use of simulation in that field, right? So suppose you're building an electric car, right? And you say, I want to build an electric car with a range of 1,000 miles and 0 to 60 in 1 second. You start with a system level specification of that product. And then essentially you do a conceptual design, some preliminary design, some detailed design using AC induction motors, how many stators, et cetera. And at that time, people use simulation, right? And so it is in that context that I want to talk about simulation. And Alberto did a fantastic job yesterday talking about how multiphysics simulation is changing the world, right? And in this world of multiphysics simulation, it is more complicated because we are sort of working on second-order partial differential equations, which is more complicated than the first-order sort of ordinary differential equations that the world of EDA, right, with SPICE works on. So it's very hard, very complicated, very, very computation-intensive. So what this picture shows on the bottom is the kinds of multiphysics simulation that is needed in areas like automotive, in aerospace, in different areas, right? So structural simulation, fluid simulation, electromagnetic simulation, and others. In that area, I want to talk about the use of AI/ML. So there is sort of two broad areas. One is to use simulation to improve AI, and the other is use AI to improve simulation, right? So in the last 40, 50 years, we have done a lot of work on improving simulation using finite element methods, finite volume methods, different finite difference time domain methods. And the researchers in sort of the AI community have done work on AI and machine learning and deep learning, supervised learning, and so on. So what this field is essentially trying to do is combining the two, right? So use of simulation, right, essentially is creating synthetic data to make the AI much smarter because AI is based on training data, and simulation can allow you to do all kinds of sort of scenarios, right, for, say, autonomous driving. But today in my talk, I'm going to use sort of AI/ML to improve simulation. We have been working on this topic for many years now, and again, many researchers at DAC and other places have been publishing papers in this area. What I kind of sort of would categorize is the work in AI/ML applied to simulation has two broad themes. One is to make the solvers go much faster, right? Because the solvers using these second-order partial differential equations can take, for a single physics, 1,000 hours to run. For two physics, the interaction may take 1,000,000 hours. The three physics would take even more, right? So how do you speed it up using AI/ML? So that's one broad area. And the first three categories, top-down methods, bottom-up methods, and reduced-order models, are all trying to improve the solver acceleration. And I'm going to share with you some early work in this area. The fourth pillar is all the excitement that we see this year around ChatGPT and large language models. This area is actually going to impact the ease of use, the solver settings automatically, right? Where you can tell a solver, right, in a natural language, hey, Fluent, please run this thing for external dynamics, and it will set all the sort of settings of Fluent completely automatically, effectively combining all the PhD level knowledge of aerospace engineering. So let me, in the next 4 slides, give you examples of each of these areas. So the first one is the top-down method. So top-down methods, basically what it does is it takes a solver as a black box and essentially runs it multiple times for different input conditions, different boundary conditions, and uses that to train an AI model. And then basically you do it for 100 runs, it learns that particular use case, and the 101st run, it runs much faster. So we have a platform called optiSLang at Ansys, which essentially allows users to do what is called design space exploration. So I'm not going to go into the details, but essentially it is a framework, which is an on-premise framework, right, to connect up different tools with multiple workflows and so on. And for that particular use case, you can run hundreds of different designs, and essentially the AI learns it and runs it much faster. So what these 3 quadrants are showing is optiSLang applied to iSpec to do thermal modeling, optiSLang applied to Red Hawk SC to do power integrity modeling, and optiSLang applied to electromagnetic simulation. But this is an on-premise, and it is actually a workflow that you can use today. What we are working on is a very exciting work on, we are essentially taking all our solvers, putting them on the cloud, right? So on that cloud environment, right, what we are saying is, suppose you have a user who has run 100 runs of, say, Ansys Mechanical, or 100 runs of Fluent, or 100 runs of HFSS, right? Can, for that particular initial condition, boundary condition on the cloud, can you essentially train the AI on the cloud and maybe run it much faster? So we are essentially creating a machine learning-based cloud-first platform, which has sort of 3 broad categories, which is the engineer mode, where the engineer has no clue about AI, right? Just uses different settings and pre-trained models. The next one is sort of a data science mode, where essentially you have heard about reinforcement learning, GAN learning, CNNs, and so on. You can, with a drop-down menu, use it. And the third one is essentially you are a real geek. You know about Python, and you can sort of go in and code sort of TensorFlow and PyTorch and so on. So all of those things are actually available on this. So it's a platform which is called the SimAI platform. And again, very, very exciting areas. Both these approaches, though, are limited to the specific use cases, right? For this structure, for this solver, I'm going to run it. For the general use cases, it does not work. So if you train it with spheres and rectangles, right, and then you give it a car shape, it will sort of fail because it has not seen that car shape before. For the general use case, you need what is called the bottom-up solver, right? This is close to the physics, and this is what Alberto mentioned yesterday, right? Going to the physics informed, right? So this is basically saying that when you're running things like finite element methods, finite volume methods, and so on, you actually go close to the solver. And so in this particular case, what we have done is we take this sort of high-dimensional problem, say in Fluent, and automatically break it down into a lower dimensional problems, like an 8 by 8 by 8 or 16 by 16 by 16 pixels, and within that area, try to understand the physics, the physics of external aerodynamics, right? So it's a general approach, and what is shown on the top right is how we have used this ML-based solver, which runs 100 times faster, 1,000 times less memory, and it's just an absolutely amazing kind of technology, right? Which will be brought to market by Ansys very, very soon. The third category of running solvers faster is reduced order models. And essentially, this goes back to the fundamentals of matrix algebra, right? All the finite element methods, finite volume methods, etc. You reduce the problem into solving AX equals B, right? You have a matrix, vector multiplication, you're trying to solve for X. The challenge is this AX is massive, right? It's 1 million entries, 10 million entries, 1 billion entries. So the number of unknowns is huge, and that's why it takes such a long time. Now, it turns out in matrix algebra, you can take these things called model order reduction, reduced order models, right? That takes that 10 million unknown problem into 1,000 unknown problem. If you can do this for, say, static ROMs, dynamic ROMs, linear transient ROMs, nonlinear ROMs, there's a whole bunch of technologies that are being cooked. And essentially, the way you train these things is very similar to sort of AI training, right? Again, we have, so the top right is showing an example of a ROM for Fluent, something that for the full PD would take 3 hours to run, can run in a matter of seconds, right? Again, another fantastic technology in the area of sort of, in this broad area. So I gave you 3 examples of solver acceleration. Now let me talk about the excitement around ChatGPT and large language models. What this is doing is, it turns out that in the world of simulation, right, You almost require a PhD in aerospace engineering to set all the settings of our Fluent solver, for example, for fluid dynamics, or HFSS for electromagnetics. You really need to know exactly what settings to use to get it to run in the most accurate way, the fastest way that will converge all the time. It turns out a large language model can sit through all these things and say, for this setting, use this setting, use this. So for example, we have actually demonstrated in the lab, right, in the city office, that you can say, hey, AEDT, right, please run this. I would like to run a sort of pre-processed harmonic analysis, right, in English, natural language, and it runs the thing, does this Ansys thing, scripting, right, and sets the solver up, and out comes a solver which runs as efficiently as a human designer, right? This is the future of AI/ML. So what I wanted to kind of highlight to you is this is not just sort of fancy stuff, all theoretical. We are actually bringing AI/ML technologies into our products. In fact, if you visit our booth, 1539, right, in the first floor, I would encourage you to kind of see in action some of these kind of stuff. Again, I don't want to go through all these things, right? So in the platform area, ML-based methods for optiSLang, right? In the digital twin area, how we are using what is called hybrid digital twins to do fusion modeling to get much higher accuracy of digital twinning. In the fluids area, ML-based, this fluid solver, the turbulence modeling for Fluent. In the semiconductor area, which is sort of the audience of this, again, we have a tremendous amount of innovation. In fact, we have Norm Chang here in the audience. He is an Ansys fellow who just got the IEEE fellow. He is leading a lot of activities in AI/ML at Ansys, and all the work on data-driven sampling for parasitic capacitance and on-chip power grid optimization is all sort of done by him and his group. So lots of exciting innovations. Now, I want to wrap up my talk by acknowledging the fact that this is an ecosystem play, right? You have seen so much innovations happening in this ChatGPT, large language models, and so on, and all the cloud providers are working on them, right? So we are working, again, we are taking our solvers and putting them in the cloud. So we have very strong collaboration with Microsoft, right, on their Azure cloud, strong collaborations with AWS, strong collaborations with Google. As you know, on Google, you have these sort of TPUs, tensor processing units, and it can be used for sort of AI/ML training and deployment. So we have got actual research collaborations going on with all the major cloud providers. Then this whole ChatGPT thing is enabled by, again, Alberto showed this fantastic picture of this convolutional neural networks, these 5 stages of neural network. Those things actually run much better on GPUs. So you need GPUs to do this. And in GPUs, there's all kinds of architectures that are going on, right? So as you know, Jensen from NVIDIA talked about this, the H100 system from NVIDIA, right? So we have collaborations going on with NVIDIA, right, as to take these AI/ML models and make them run much faster on the NVIDIA GPUs. AMD just announced their MI300 GPUs, right? So Intel announces, so we have got collaboration going with all those people, right? With Mark Papermeister at AMD and others, right? And Sanjay Chowdhury at NVIDIA to make sure that these things work best on the GPUs. And then you have a whole bunch of startups in this area. And I'm just giving a sampling of startups that we are working on. Neural Concepts based in Switzerland, Extrality based in France. So again, this area is very, very rich. And of course, all the academics that are sitting here, and it's a subset of universities that we are working on that I want to acknowledge here. Professors from Stanford, from MIT, from Carnegie Mellon, and a few other places. So thank you very much for your attention. I personally think that AI/ML is one of the most disruptive areas in EDA, and specifically in simulation. What I tried to capture in a very short 15-minute talk is the exciting opportunities for solver acceleration in the 3 areas, top-down methods, which is very easy to use. You can use a black box solver, but it works for narrow use cases. For the use case you train it for. The bottom-up methods are physics-informed. They understand the physics, very general, but it's harder to develop those methods, right? And I kind of showed you an example of an ML-based fluid solver. The reduced order models are very mathematical. They're very general approaches, but again, have been around for some time, right? Which I kind of mentioned. And then the use of large language models, ChatGPT, to essentially make all these solvers and so on much easier to use. And that is a very general thing, can be applied to a whole bunch of sort of EDA technologies. Again, I just wanted to say that, just as I said, 40 years ago when I started working on HPC and parallel CAD, right, it took 40 years for Ansys to make significant business impact. I am sure this AI/ML area that all of you are working on in the research tracks, I'm going to sit through many of the presentations, will actually make business impact very soon. So thank you very much for your attention.